So in this video, I just wanted to briefly introduce you to the concept of the total response of RLC circuits. And what we're going to find is that this is very similar to the concept that we talked about in the prior chapter for first order differential equations. Namely, we can always conceptualize the response or the solution to any differential equation as the sum of the force response, which is going to be kind of dominant in the long term and due to the actual sources present within the circuit, plus the natural response. And the natural response is just the source-free response. It is associated with the energy stored in the circuit as a function of the initial conditions. So as we saw in the prior chapter, determining the force response is relatively trivial because basically all you're doing is doing the same type of steady state analysis that we do when we draw the circuit for t equals 0 minus. Really, the only challenging part of this is finding the natural response. And really the only challenging part of finding the natural response, as we've seen in all the videos we've done so far, is determining the relevant initial conditions. Because if you think about it, even determining your complex frequencies and just selecting the particular form of the general solution in the cases of overdamping, underdamping, and critical damping is just a matter of looking things up out of a table. So the real challenge just is getting in the habit of determining those initial conditions. The one thing that I do want to note is just like the prior chapter, when we have those unknown constants in our total response, which is the force response plus the natural response, you can't determine them until you can't determine them solely for the natural response like we've done so far. The entire response has to satisfy the initial conditions, so you don't solve for those parameter values until the end. And this just walks you through the process, and I think it's good to go through and look at an example in the textbook, but what you're going to find is that it's going to be very similar to everything we've done up until now. And given that we're in an accelerated course, the value of spending additional time on this isn't as much as you'll get by us getting farther into the AC circuit analysis content. So that's why I'm not going to do an additional example of this, but just to show you how it actually works here and why it's just so important to focus on being able to solve for those initial conditions. This is the example that your text does. If you notice, you have a step function source that's turning on at t equals 0. So we have that additional DC current source over here. Before t equals 0, that is going to be off. And we have this constant 5 amp source over here as well. So in terms of just let's walk through this really quick and just ask ourselves, how would we determine the actual value of these circuit quantities at 0 minus? Well, at 0 minus, this source isn't going to be on yet. So really all we're going to have is a DC current driving really what in the middle amounts to a series combination of a resistor, an inductor, and a capacitor. And remember that once this thing has been on a long time and it's in steady state, so before this source actually turns on at t equals 0, the capacitor is going to behave like an open circuit, the inductor is going to behave like a short circuit. So really all that you have going here is a 5 amp source driving through this 30 ohm load and going through the short and coming back around. So from a circuit analysis point of view, it couldn't be simpler. All of this current is just going to pass through the resistor, then go through the inductor, which is acting like a short circuit, and circulate. So at IL of 0 minus, of course, that's just going to be 5 amps because that's the way that the current is going. Since they've defined the direction of IR going the opposite direction, IR is just going to be minus 5 amps. So again, that's just a consequence of the direction that they've defined. And since the capacitor is behaving as an open circuit, IC at 0 minus will be 0. How would we then subsequently determine the voltage across the resistor before this source turns on? Well, Ohm's law still holds. You know the current through the resistor, multiply it by the resistor value, and that's what you get. You notice that it is negative subsequently because the current is negative. Of course, if the inductor is behaving as a short circuit has 0 resistance. There's not going to be any voltage drop across that. When the inductor is acting as a short, what you see is this resistor is actually in parallel with the capacitor. So whatever VR is, that's going to be the value of VC. But note that the polarities when you drop that in parallel are different. So VR technically is minus VC. So that's where these are coming from. What happens right when you actually turn this additional source on? Well, the way you do this is first you enforce your continuity, thinking about the things that can't change. Those are your inductor current. So if you notice your inductor current remains the same, and your actual capacitor voltage values. And then typically what you're doing is doing some sort of circuit analysis in order to determine the actual rest of the quantities. What makes the second order one such a pain, as we've seen through all the examples we've worked on now through up until this point, is you not only have to determine the initial conditions, but also the values of their derivatives. And usually that's just applying circuit analysis the same way that we've done in all the examples up until now, where you're trying to find the derivative of a particular function, and you have to relate it back to another quantity in the circuit. And I know if you haven't watched these videos yet, that won't make sense with respect to what I'm saying, but hopefully you can walk through like an example like this and be able to just follow along with what they're doing. I'm not going to ask you any questions about forced responses on either the homework or the exam, but I think it's important to know. So just one thing I should have said in terms of the actual forced response here. Once this circuit has been on for a long time, right, you're going to have both this 4 amp current along with this 5 amp current driving through the circuit. The capacitor is going to start to act like an actual open circuit again, and this will eventually act like a short circuit again. So what you're actually going to find there is that all of this current in the steady state will just circulate through this short. This current is going to go totally through the 30 ohm resistor when this acts as an open circuit, and then circulate back by the short. So the reason this is 150 again for the forced response is that basically in steady state, the only this 5 amp current is only going to go through the actual none of it's going to go through the capacitor because it's open. It will just go through the resistor. This is a short circuit. It's the same argument for the 0 minus conditions. This VR basically drops in parallel with the VC value. So that's why the forced response here this is 150. The one thing I wanted to say, in addition, it's important to know, is what happens if you take the resistor out? Well, we know that the resistor serves as the damping mechanism within the circuit. So what you will find is if you analyze these circuits absent of a resistor, they're just going to purely oscillate. They won't exhibit that exponential decay. So that's all that the text is showing you here, is if you short out the resistor in a series RLC circuit, or you make it infinite, thereby removing it in a parallel RLC circuit, the underlying response of the circuit is just going to be sinusoidal. You're never going to have any damping. So I know this is a tough chapter, particularly when you're trying to cram through it all in 1 week, and that 1 week is part of a shorter 8-week course. However, hopefully just really focus on those examples that we went through in the actual lecture videos, and you will be good to go on both your homework along with the exam.